Okay, what if I told you that falling into a black hole isn't just, the end? That it's actually a journey, a mind-bending trip into the most extreme physics the universe can throw at us.
Hmm.
We're talking about a place where time warps, space literally stretches, and reality itself gets, well, twisted.
Completely.
So today, that's our deep dive. We're going step by step into that cosmic abyss, our mission, to figure out what really happens if you fell into a black hole, using everything we've gathered to give you the clearest picture we can.
It really is an exploration to the edge, isn't it? The very edge of what we understand scientifically. It's a place where the physics we rely on day to day, they just start to unravel.
They break down.
Exactly. You're confronting the ultimate cosmic unknown. It's quite a thought experiment.
It absolutely is. And look, don't worry, it sounds intense, and it is, but we're going to walk through this together. We'll make it understandable. And honestly, there are some genuinely surprising facts, some real aha moments in here. Ready? Let's unpack this cosmic plunge. So, as you get closer, what's the view like? Our sources paint this picture of a perfect dark circle against the stars.
Right, the void itself.
But that's where normal kind of stops, right? Around it, the stars aren't just fuzzy. They're smeared, warped, wrapped around the darkness like light in a funhouse mirror.
It's gravitational lensing taken to the absolute extreme. Light bending in ways that are hard to picture.
And you'd feel it too, wouldn't you? Even far out. A pole.
Oh, definitely. You'd start feeling that immense gravitational tug. Maybe subtly at first, but noticeably even millions of kilometers away, and visually. Before you hit that critical point, you'd likely see the accretion disk, if there is one, of course.
That glowing halo.
Exactly. It's not just dust. It's gas and shredded stars swirling incredibly fast, heating up hotter than the surface of stars. It's this blazing, radiant ring, a very visible sign of the sheer power you're dealing with.
Wow. Okay, so you see this superheated disk, you feel the pull getting stronger, and you know you're getting close to the boundary, the event horizon. But it's not like a wall, is it? What actually is the event horizon?
That's a really crucial point. It isn't a physical surface you could, touch or bounce off. It's an invisible boundary. Think of it as a mathematical line in spacetime. Once you cross it, the speed you'd need to escape, the escape velocity, becomes greater than the speed of light.
And nothing's faster than light.
Precisely. So nothing, not even light, can get back out. But here's the really fascinating part. Your experience depends completely on where you are.
Okay, how so? You mean someone watching versus the person taking the plunge?
Exactly right. For a distant observer, watching you fall in, it's totally different.
Yeah.
From their perspective, time for you would seem to slow down dramatically as you approach the horizon.
Slow down how?
Like almost grinding to a halt. They'd see your image appear to hover right there at the edge, getting fainter and redder, never quite seeming to cross. You'd look frozen, like a silhouette stuck at the boundary, slowly fading away.
Frozen forever. But for me, the one actually falling, it's business as usual.
Well, usual might be pushing it, but yes, in terms of crossing that specific point,
Yeah.
it would be surprisingly unremarkable. There's no cosmic doorbell, no barrier. You just pass through.
Huh.
But the instant you do, you gain this absolute irreversible knowledge.
Yeah.
Every single path now leads inwards,
Yeah.
downwards. There's no turning back. Your future is now entirely inside the black hole.
That difference in perspective, it's genuinely hard to wrap your head around. And okay, here's something that really blew my mind from the sources. Your physical experience right at that horizon, it changes depending on how big the black hole is.
Yes, this is a key distinction. It dramatically changes what happens right at that point of no return. Let's say you're falling into a stellar mass black hole, one formed from a collapsed star, maybe a few times the mass of our sun.
Okay, a smaller one, relatively speaking.
Right. In that case, the tidal forces the difference in gravity's pull between, say, your head and your feet become incredibly strong. Even outside the event horizon, you'd likely be stretched apart, spaghettified, before you even got to the horizon.
Spaghettified. So you wouldn't even cross the point of no return in one piece.
Probably not. Your journey would end pretty violently, quite far from the center, relatively speaking.
Ouch. But what about the big ones, the supermassive black holes?
Well, that's a completely different story. These are the giants at the centers of galaxies, millions, even billions of times the sun's mass.
Yeah.
Their event horizons are enormous, millions of kilometers across.
Right.
Because they're so huge, the gravitational difference across your body at the horizon is much, much smaller. The curve of space-time is gentler there. So crossing the event horizon of a supermassive black hole might actually feel, almost ordinary.
Ordinary. Falling into a black hole.
At that precise moment, yes. You might drift across without noticing anything immediately catastrophic. The point of no return would slip by unnoticed initially.
That's astonishing. One type rips you apart before you get there. The other lets you drift across like nothing happened at first. But
Quickly.
regardless of which type you fall into, that initial crossing doesn't save you from the ultimate fate deeper inside, does it? We still have to talk about spaghettification.
No, it doesn't save you. The scale just dictates the immediate experience at the horizon.
Yeah.
Deeper inside, as you get closer to the center, those tidal forces become immense in any black hole. And spaghettification.
Yeah.
Yeah, it sounds almost funny, but the reality is absolutely terrifying.
It's cosmic horror, really. Your body just stretched out like taffy,
Yeah.
like pasta. Molecules torn apart.
That's the physics. The part of your body closer to the center is pulled so much more strongly than the part farther away. That difference in force, the tidal force, stretches you vertically while squeezing you horizontally. You'd become an incredibly long, thin stream of atoms, basically.
Yeah.
Not a pleasant thought.
Not at all. And then there's the time thing again, this time dilation aspect. So for me, falling in, my watch ticks normally. 1 second is 1 second. My thoughts feel normal speed.
Correct. Your local experience of time continues as it always has.
But for that distant observer, the one who saw me freeze at the edge, what happens from their viewpoint after I cross, even if they can't technically see me?
From their frame of reference, as you fall deeper, your time continues to dilate infinitely relative to theirs. The implication is profound as you experience your final seconds or minutes falling towards the center. Billions, maybe trillions of years could pass in the outside universe.
Billions of years.
You would, in a sense, witness the future of the entire cosmos flashing before your eyes in your final moments.
So I see the universe age and die while I'm falling.
Effectively, yes. The universe outside races ahead. It really makes you question, what even is normal time in these extreme situations? It's all relative.
It just completely breaks our everyday intuition about time being this constant universal thing. It's not. Okay, so spaghettification, time dilation. But what about the very end? What happens after crossing the horizon, heading towards that center? This is where things get really fuzzy, right? Science doesn't have firm answers here.
No, it doesn't. This is where we hit the limits of known physics. Our current theories, like general relativity, predict a singularity at the very center.
The point of infinite density.
Theoretically, yes, a point where all the mass is crushed into zero volume. But infinities like that in physics usually tell us one thing.
That the theory is incomplete.
Exactly. It signals that our understanding breaks down. Is it really an infinitely dense point? Or is that just what our current math says because it can't handle the extremes? There's a big debate. Maybe quantum mechanics, which governs a very small, steps in somehow.
How so?
Well, quantum theory doesn't really like infinities or singularities. Some ideas suggest that instead of a point, you might get some kind of exotic quantum state of matter or space-time, something we just don't have the physics to describe yet.
So it's not just a boundary in space, the event horizon. It's like a boundary for our knowledge.
That's a perfect way to put it. A boundary of knowledge for humanity.
But beyond the, let's say, mainstream physics, people speculate about even wilder stuff, don't they? Things from the sources like wormholes, parallel universes.
Oh, absolutely. When your established physics breaks down, it opens the door to speculation, some grounded in theoretical possibilities, some more out there. The idea of wormholes, tunnels through space-time, potentially connecting distant parts of our universe or even other universes, sometimes emerges from the complex mathematics of black holes, especially rotating ones.
Like a shortcut through the cosmos.
Potentially. And then there's the information paradox, the question of what happens to the information about the things that fall in. Does it just vanish? Some theories, like the holographic principle, suggest maybe the information gets encoded somehow on the event horizon itself. So in a weird way, a version of you might never be truly lost.
Oh, okay, that's a lot to think about. It feels like these things should be permanent fixtures, these cosmic drains. But then I read about Stephen Hawking, and suddenly maybe they're not forever.
That was a revolutionary idea. Hawking showed that black holes aren't perfectly black. Due to quantum effects near the event horizon, they should actually emit a faint thermal radiation.
Talking radiation.
Exactly. And emitting radiation means they're losing energy. And since energy and mass are equivalent,
They're losing mass. They're shrinking.
very, very slowly,
Oh.
over absolutely unimaginable timescales, eons upon eons. But yes, they evaporate.
So they're not eternal prisons after all. They have a lifespan, just like stars and galaxies. How does it end?
Well, it depends on the size. For tiny primordial black holes, If they exist, they could evaporate relatively quickly, possibly